So to do the exercise, we start with a geometry that looks like this. It's just a rectangle 1 meter across by 2 meters long, and we have fluid coming in here and here. It's the same reaction that we used before, except in this case, compound A comes in here and compound B comes in here, and they're both coming in at a flow velocity of 1 millimeter per second. And so these compounds, these solutions come in here, they mix inside of this chamber, and then they flow out right here at this point. And so the problem is to do an analysis and find out what the production rate of compound C is when it undergoes a reaction in here. And then what I want you to do is try to understand what's going on internally. How are these two streams mixing together? Where is the reaction taking place? And then go in and try to modify the reactor by putting in some baffles and modifying the flow to see if you can boost the production rate of compound C as it undergoes reaction. So let me show you some details about how this is set up. What I'd like you to do is set it up yourself set it up for yourself from scratch. I'll show you how I set it up, and this file is available if you want to refer to it. But try to set it up on your own from scratch, the extent that's possible. So the geometry is pretty straightforward. It's a rectangle and a few points shown here. The definitions, they're shown here. And what I want you to do is, we recognize these from several classes ago. These are just the variables to specify the chemical reactions. And then these refer to some functions that we've described. Actually, one integration function where we do a line integral along the outflow. And what I've done is to take this file here, take these variables, and I went here and save them to a file. So when you go and set up your model, you can import these variables, and they'll look just like this, and that'll save you having to type in these different values. So then you'll get you'll start with the same values that I started with. You'll have to go and set up this integration function, and in order for these variables to work, you have to have something that's called integrate outflow, all lowercase. And so here's integrate outflow. It's a integration across a boundary, and it's that boundary, number 6. And it's called integrate outflow. That's all there is to it to set that up. Okay, so we can take a look. I think everything else is fairly obvious. Take a look at the setup of the transport analysis and its convection. We have the diffusion constants are shown here, and we've got diffusion, and actually this should be D as well. Let's see. I kept that as D 1000. So what this would be is C will be precipitating out as a solid. So it'll be small granules of solid that would, say a colloid, that would move with the flow but would not diffuse. So we'll keep that as D divided by 1000. So initial values, in this case, they'll be all zeros because we're going to be injecting the two reactants. The reactions, same as what we've used before, inflow, and now we have to have two inflows for this case because this is the inflow for the transport problem, and we have A coming in here, so we specify it as A0 as that variable name, and up here it'll be B0, and outflow is just the outflow condition for that boundary. So for the laminar flow problem, fluid properties of water, these are just defaults, and in this case we specify both of these as inlet with the same velocity of 0.001 meters per second, and that's the outlet right there. So the mesh is pretty straightforward. Made it a finer mesh just using the default triangular mesh. So when we run this, the flow analysis this is set up really the same way that the example was set up, and if we take a look here, we see that the laminar flow is checked. Under transport, the transport is checked and laminar flow is not checked, and values of dependent variables we have making use and getting the flow system from the stationary analysis. Okay, so fair enough, we ran this. First of all, I ran the flow, then I ran the transport, and we can take a look at the results that we got. So there's the velocity distribution, and we see that we have these streams that we're injecting, and they go and merge together right here, and we've got a eddy here, one here, and one here. So that seems like a reasonable velocity distribution. Pressure, there's some pressure contours. Not sure that's really too useful. And the concentration distribution. This was somewhat surprising. See, let's go down here and take a look at the player. So if we take a look and advance this, well, let's take a look at the velocity here. What I thought was going to happen was we inject these two compounds, and they come and they come together here, and this is where the mixing is taking place, and so this is where the reaction would happen. As it turns out, that's not the case at all. The reaction rate for this chemical reaction is slow enough so that the fluids just aren't in contact long enough, the species aren't in contact long enough here to really react and produce much compound C at all. And so what happens instead is these eddies are where the action happens. So we have some A coming in here, and A gets trapped in this eddy, and B gets trapped in here, and they swirl around and they diffuse together and mix together, and this is where the reactions are taking place. And so we can see that from the player. Start out here, and as time progresses, we can see just some low concentrations forming, kind of marking these eddies, and then it increases time, and there it is progressing with time. That was white there because we had a little bit of a negative concentration, and I've adjusted the plot so that anything below 0 is white. Okay, so this is the final distribution of the concentration of C, and you can see this is where the highest concentrations are. And so apparently what's happening is you can see this dark band up here. That's the main flow, and that's actually got the lowest concentration of C in it. And so what's apparently happening is that you have a concentration of C here in this eddy between the two flows, and that's a fairly high concentration, and some of it seems to be getting swept out and moved along here. This light blue band could also be from these two streams coming in contact. So a much different pattern than I was expecting. I thought this is where the action would be, but as it turns out, because of the slow reaction rate, the main concentration of compound C is right here in these two eddies that are formed between the two inlets. So we can also check out the mass rate out. This is what it looks like. This is the concentration, or this is the mass flow rate of concentration C. And so it rises quickly and then levels out and hasn't quite reached equilibrium, but it's flattened out here at, say, roughly 40 times 10 to the 8th moles per meter per second. This is a 2D model, so if we multiplied by unit thickness, then the units would be moles per second. Okay, so this is kind of a baseline result, 40 times 10 to the minus 8. So what I want you to do is set this problem up like I've set it up here, and then see if you can adjust the design of the reactor to get a better mass rate out. And so here's what I tried. I said, well, let me put in a rectangular baffle. So I set it up already, and it looks, enable it, and it looks like that. Okay? And so that'll be a wall, and we'll have the flow go around that wall. So here's what has to be done in order to get this to work. We put that thing in there, and then we go here to this interface, and the default is that both these subdomains are active. But what we need to do is go here to the main tab on the interface and turn this off. Okay, so now these physics are active in this subdomain, but this subdomain here, the baffle, it's simply inactive. And we do the same thing for laminar flow. Turn that off. And we can remesh it. In this case, we have the mesh go through here. We could also turn this off and not have the mesh go through here, but it's a fairly small area, so it doesn't really matter for this particular case. So now when we run it, we'll run the flow, and we'll see that this baffle changes the distribution of the velocity quite substantially. So now we have the flows converging here and forming a jet. It goes along and exits there. So makes sense. We see we have now two of these eddies right here and here, and we would need to run the transport analysis again. This analysis takes about 90 seconds on this computer, and so I won't run it again to show you the result. But what's going to happen is we have a band here where the two primary streams mix, but then also we've got mixing in these two eddies and production of mass there. And so as a result of this fairly complicated pattern of mixing where these reactions would take place, we do get a higher mass rate. One thing, though, that's important to keep in mind when we do this is to make sure that these zones are turned off and made inactive. Otherwise, you'll have the flow go right through this region. You can also, you could turn off the flow, but have the transport go through this region, and in which case you would have mass flowing or moving through this in an anomalous way. So just make sure that you do that, you turn both of those regions off. So what I want you to do is experiment around. Use your imagination and put in baffles of different configurations. see what you can do in terms of boosting the mass production rate. Now, of course, when you put baffles in, you're going to cause more resistance to flow, so that will also be a consequence. And what I haven't done is put a restriction on the pressure that is required to move this water, move this flow rate through the reactor. So because there's no constraint on the pressure, I guess limit yourself to say 4 baffles, no more than 4. And so give it a try, see what kind of mass rate you can come up with.